Today's lesson, hypothesis testing about a population proportion. Let's start with this problem. An auto safety expert stated that fewer than 68% of drivers regularly wear their seatbelts. A study was conducted to determine whether this claim seems to be correct. This study determined that out of 259 randomly selected traffic stops, 162 drivers were not wearing their seatbelts. With a 94% level of confidence, test the claim that fewer than 68% of drivers wear their seatbelts. There are several things that we have to do in order to do a hypothesis test. We will need to determine whether this is a test of mean or proportion. After that, we need to determine the correct sampling distribution, just like we did for confidence intervals. Determine if this test is a left tail, two tail, or right tail test. Set up the null and alternate hypotheses, and I, of course, will explain all of this. Determine the critical values and rejection regions. Sketch a diagram of the distribution showing the critical values and the rejection region. Calculate the test statistic. Place a mark on the diagram you've already drawn where the test statistic should be. Compare the test statistic to the critical value or values to see if the test statistic falls within the rejection region. Conclude whether we reject the null hypothesis or fail to reject the null hypothesis. And state the conclusion in layperson's terms. Before we do any of this, one thing that we need to do is deconstruct the problem. In other words, there's a bunch of numbers and information in the problem, and we need to just break it apart so that we can get to the heart of the matter. And then we'll do those steps A through K. The first thing is we have X, and for hypothesis testing of proportion type problems, X represents the number of things or people from the new sample that match the criterion under consideration for the problem. In this problem, for example, we are concerned with those that are not wearing their seatbelts, or X equals 162. In other words, here's my sample. It determined that out of 259 randomly selected traffic stops, 162 drivers were not wearing their seatbelts. And because that's the topic under consideration, those not wearing their seatbelts, then X would be 162. N is the total number of people or things in the sample. In other words, this study determined that out of 259 randomly selected traffic stops, that 259 is the total number of traffic stops or the total number of things or people for this problem. Now we have this P with this little thing above it. The name for that is called P hat. In other words, the letter P and then the word hat, like it's wearing a hat. And we calculate P. It's a quick and easy calculation, so that's why it's part of the deconstruction process and not part of the actual hypothesis testing part. P hat equals, we take the number of things or people that match the criterion, and we divide that by the total number of people in the sample. In other words, X divided by N. This gives us the proportion of people or things that match the criterion under consideration for the sample. So for this problem, P hat equals 162 over 259, or 162 divided by 259, which is approximately 0.62548. You have a Q hat. Q hat is equal to 1 minus P hat. For almost everything that we do in statistics, a Q is always a 1 minus P. And for this problem, Q hat is equal to 1 minus 0.62548, which is equal to 0.37452. At some point, we are going to put all of these on a spreadsheet so that I can show you what it all looks like. But for right now, just accept my calculations as truth. P is equal to the proportion of people or things that is commonly accepted as truth. This is usually what a previous study or survey showed as the proportion of people or things that match the criterion under consideration. We always test against this number. For this problem, P is equal to 0.68. It says right here, an auto safety expert stated that fewer than 68% of drivers, so this is P, and this is what we're going to end up testing against. Q is simply 1 minus P, so Q is equal to 1 minus 0.68 or 0.32. We have our level of confidence, again, similar to confidence interval problems, and we express our level of confidence as a decimal, and for this problem, it is given to us directly in the problem. It says with a 94% level of confidence. By the way, the same thing holds true for hypothesis testing as confidence intervals, and that is if there is no level of confidence given or no easy way to just figure it out. For example, you might be given a level of significance. If none of those two things are given, we have a default level of confidence of 95%. So remember, 95% is considered to be the default level of confidence if none is given in the problem. Alpha is 1 minus the level of confidence. It's the same as it was for confidence intervals. This is also called the level of significance. For this problem, alpha equals 1 minus 0.94 or 0.06. Here's basically what we have. I'm just going to read it off quickly. X equals 162, N equals 259. P hat, which is X divided by N, is 0.62548. Q hat is 0.37452. P, which is again what we consider to be truth, unless this study that we just conducted can show us otherwise. Q is 1 minus P, or in this case 0.32. Level of confidence is 0.94. Alpha is 1 minus my level of confidence, which is 0.06. And we might or might not need alpha over 2. So let's continue with the problem and start working through the hypothesis test by doing all the steps A through K. Determine whether this test is a test of mean or proportion. Well, basically it's a proportion, and it should be obvious. When we're talking about percents, it's the same basically as proportions, and that's the bottom line. This problem is a test about population proportion. The key words to look for are proportion or percent. Determine the correct sampling distribution that should be used. Similarly to confidence intervals, if it is a test of proportion, the correct sampling distribution that we use is the standard normal. Part C. Determine if this test is a left tail, two tail, or right tail test. This is one of the more difficult things for some reason. You have to look for keywords. There's no easy way of doing it. You have to read into the problem. The problem gives us information. But look for keywords, and one keyword to look for is fewer than, or less than, or maybe greater than, or more than, or anything like that. Or sometimes it'll say is different from. But in this case, it says to test the claim that fewer than 68% of drivers wear their seatbelts. Since our keyword is fewer than, it indicates that this is a left tail test. Anything fewer than, less than, etc. would be left tail. More than, greater than, increasing would be a right tail test. And we'll talk about two tail tests in a little bit. Set up the null and alternate hypotheses. We have special symbols for all of this. So let me just get to it. This H with a little 0 next to it is considered to be our null hypothesis, and this H with a little 1 is considered to be our alternate hypothesis. The null hypothesis for a test of proportion will always get P equals. It's because that's the number we're testing against. Since this is a left tail test, and we determine that by the keywords fewer than, our alternate hypothesis is P is less than 0.68. Now, this had been a right tail test, it would have been the exact same thing, except this less than symbol right here would have been a greater than symbol. If it was a two tail test, it would be a not equal to symbol, which looks like an equal to symbol with just a line through it. But this one is a left tail test, so my alternate hypothesis is P, or the population proportion, is less than 0.68. Now we have to determine something called the critical values. Critical values are determined by the level of confidence or the level of significance. Again, they're pretty much just complements of one another. And the correct sampling distribution. We have used the correct sampling distribution for this previously, and it's on a spreadsheet, the norm.s. For this one, because it's a one-tail test, we simply do norm.s.inv of alpha. We do not use the alpha over 2 value because we're not splitting it up into two tails. This is simply a one-tail test, so we only use alpha in that function. Now that will give me a negative value. No matter what, it's a negative value. That's good for a left tail test. If this happened to be a right tail test, then we would use the positive of that value. But it's not a right tail test, it's a left tail test, and we will use the negative value. And I already put it on a spreadsheet, and I have the correct number. And basically, this whole thing just says what I said. It's determined by the level of confidence or level of significance. And for a left tail test, we use the Excel function equals norm.s.inv of alpha. And again, note, we don't divide by 2. For a right tail test, we would need the positive result, so we would take the absolute value of the norm.s.inv of alpha. And a two-tailed test would give us 2 critical values, and I know I haven't explained what critical values are yet, but we would use both the positive and the negative result of the norm.s.inv of alpha over 2. And note, for a two-tailed test, we do divide alpha by 2. So for this problem, our critical value is norm.s.inv of 0.06, because that's what my alpha is. Or my critical value, after putting it on a spreadsheet, ends up being approximately equal to negative 1.555. So that's parts A through E of this hypothesis test. This is what we have so far. We have all of our deconstruction part up here. We know it's a test about a population. We know the correct sampling distribution is the standard normal distribution because it's a proportion problem. The key words fewer than indicates that this is a left tail test. My null hypothesis is P equals 0.68. My alternate hypothesis, because it's a left tail test, is P is less than 0.68. We got our critical value of negative 1.555. Now, this is the diagram. My rejection region starts somewhere about here. And I know I haven't explained what rejection region means yet. We'll get there. The critical value is negative 1.555, which is right about here. And what that is, that's a boundary. That tells me where my tail actually begins or ends, depending upon how you look at it. And depending upon my level of confidence, that boundary will change. It'll move to the left a little bit or to the right a little bit. But it's always somewhere, or usually somewhere between 1.5 and 2.5-ish, just depending upon the level of confidence. So again, let's backtrack a little bit and see what we have so far. We have our deconstruction part of the problem where we get all this very simple, quick calculations. We know it's a test about a population proportion, and the sampling distribution is the standard normal distribution. The keywords fewer than indicates that this is a left-tail test, with my null hypothesis being p equals 0.68, because 0.68 is truth, unless this little study tells us otherwise. And my alternate hypothesis is p is less than 0.68, and we use less than because it is a left-tail test. We know our critical value is approximately negative 1.555. And now we have to calculate something called the test statistic. The test statistic is it's a long calculation, but once we set it up for the first time on a spreadsheet, basically it's always there, and that's it. We don't really have to worry about it too much, but here's the formula. Formula says to calculate the test stick for a population proportion hypothesis test, we have p hat minus p divided by the square root of p times q over n. So for this problem, these are what the numbers look like. I'm not going to spend a lot of time doing that or doing the calculation, but what it works out to be is my test statistic is negative 1.881. Let's take a look at what we have. I'm not going to go through all of these things again. Let's just take a look at my critical value and my test statistic. My critical value is negative 1.555. My test statistic, which I have written down here, is negative 1.881. And the question is, does that test statistic fall within the rejection region? The answer is yes, it does. Now let me backtrack a little bit. Hypothesis tests are similar to the way we, theoretically run our legal system of innocent until proven guilty. Our truth or innocence would be what we commonly accept as true. In other words, the stuff that we already know. So in the case of this problem, what we accept as innocence is this 68% number. In other words, we would say 68% of people regularly wear their seatbelt. That is what we consider to be innocence, unless this study proves otherwise. It looks sort of like it proves otherwise, because when we conducted our study, we came up with roughly 62.5% of the people. But that might not be enough people in reality. If we only, say, had 10 people and roughly 6 of them were not wearing their seatbelt, 10 people is really not enough to determine that fewer than 68%. So we have this point estimate of the mean. So we have this point estimate of the population proportion, but we don't know whether it's statistically significant enough to say that fewer than 68%. And we are testing this at a level of 94%. So if it is statistically significant enough, we have this bar to reach of 94% level of confidence. Bottom line is this. All hypothesis testing boils down to the calculation of two numbers. One number is the critical value, and the other is test statistic. We compare those two numbers, and depending upon where your test statistic falls with respect to your critical value, that will tell us whether or not this test is statistically significant enough to say that within a certain level of confidence that the original claim is no longer true. So for this one, my test statistic falls in my rejection region. We are testing against that 68% or 0.68. That's what the null hypothesis is. However, because my test statistic falls in the rejection region, we end up rejecting the null hypothesis. In other words, we go back to this and we say, no, we reject that. We have statistical evidence enough to say that this is no longer our number. Now, we don't know what the exact number is. We just know that this is not the number. And we know that, or what we have just proven, is that whatever the new number is for our population proportion of those who are not wearing their seatbelt, this number, the new number, is somewhere less than 68%. For all we know, it could be 67.9% or it could be 40%. We don't know. We just know that what we have just proved is that it is no longer 68%. That's not considered the population of people who wear their seatbelts. It is less than that somewhere, with a 94% level of confidence. I just stated that again here in writing. Since the test statistic falls within the rejection region, we reject the null hypothesis. Since this is a one-tailed test, and because we reject the null hypothesis, in layperson's terminology, we can simply restate the words in the problem. Thus we have, with a 94% level of confidence, it seems that fewer than 68% of drivers wear their seatbelts. So let me backtrack a second there. If I look at the last sentence of the actual problem, it says, with a 94% level of confidence, test the claim that fewer than 68% of drivers wear their seatbelts. So in this case, down here, because we rejected the null hypothesis, we say, yeah, with a 94% level of confidence, it seems that fewer than 68% of drivers wear their seatbelts. And this is what the diagram looks like. Here we are in spreadsheet mode. And let's type in the numbers from the problem. X is 162, N is 259. Now remember, to get P hat, we simply divide X by N equals, click on the X, divided by N, and that gives me P hat. For Q hat, we would type in equals 1 minus whatever we got for P hat. Remember, P is what we explain as innocence or the truth unless this study proves otherwise, and it was 68%, so we would type in 0.68. Q is equal to 1 minus whatever P is. My level of confidence for this problem is 94%, but I will express it as a decimal. Alpha is 1 minus my level of confidence. Alpha over 2 is half of alpha, but we didn't need it for this problem, but we'll do it anyway. In order to get our critical value on the left side, what we do is we simply use the norm.s.inv function of alpha. And to get The right side, well, it's the same as the left side, it's just a positive value, and I like to use the absolute value function. And to get the critical value for two tails, it's going to be the positive and negative value when we use alpha over 2. And now we have our critical value for a two-tail, but remember, even though this test was not a two-tailed test, just remember that it will be both the positive and negative value. So the test statistic that will equal, going to open parentheses for the entire numerator, and you can put the video back to the actual formula, but it's p hat minus p over the square root of p times q over n. So this will equal, open parenthesis, we take p hat minus p, close parenthesis, divided by now you should know the square root function is just sqrt, open parenthesis. We can say p times q divided by total number of things we have, and close that parenthesis and press enter, and you can see it's negative 1.881. If I compare my test statistic to my left tail critical value, it's of negative 1.55477, etc. I can see that this falls in my rejection region. Let me go back to the graph. And here we are on the graph where my test statistic is negative 1.881 right down here. Critical value negative 1.555. The test statistic is obviously in the rejection region. I reject what I have known to be truth until this study, which means I can say for this problem that it is less than whatever I had known to be truth in the past. In layperson's terms, we would say with a 94% level of confidence, it seems that fewer than 68% of the drivers wear their seatbelts. Now that we have the spreadsheet set up, the next problem becomes pretty easy, and it certainly won't take us as much time.